I'm going to present a paper published in IEEE Robotics and Automation Letters entitled Pneumatic Quasi-Passive Variable Stiffness Mechanism for Energy Storage Applications. Our muscles can easily adjust stiffness for different actions. Thus, variable stiffness in exoskeletons is necessary to accommodate joint torques for different movements such as walking, running, or vertical jumping. It has been shown that augmentation of humans is possible without delivering positive net mechanical work to the limbs by accumulating energy in the elastic element and releasing it to support the limbs, which is enabled by clutches. However, there are some limitations in the current state-of-the-art variable stiffness actuators. In electromechanical actuators, stiffness variability is achieved mechanically, which increases complexity and can quickly culminate in bulky devices. Pneumatic actuators are suitable for exoskeletons, and the stiffness can be adjusted by pressure, but the biggest limitation is the need for a compressed air tank that limits portability. There are two main contributions of our paper. First, a novel pneumatic quasi-passive mechanism that requires a minimum power input for operation, and second, a novel method of stiffness modulation without a separate air supply. The mechanism consists of an air cylinder and three fast-switching valves. By pulling the piston rod with external force from the initial equilibrium position, highly compressed air is generated in the upper chamber, while below atmospheric air pressure is generated in the lower chamber. We assume isothermal process for an ideal gas described by the following equations, where graph in figure 2 depicts how pressure in one chamber increases while in another one decreases. We derived mathematical model of force as a function of current position, and initial pressure, where n is number of steps. Stiffness modulation is performed in steps. In the first step, initial position is set as the valve 1 is on, as this allows free movement without generating the force. In B, part of air is being sucked inside below atmospheric chamber as valve 2 is opened. In C, valve 1 is opened again to equalize the pressures between the chamber, where now the total amount of air is increased. These steps can be performed as long as below atmospheric pressure does not become equal to atmospheric pressure, after which the air cannot enter the chamber anymore. The final result is stiffer actuator. The methodology was tested on the experimental setup shown in figures 6 and 7. Two different experiments have been performed. First, modifying the initial position, where we wanted to see how valve performs the role of a clutch, where the piston rod was set to 5 different initial positions. And second, modifying the initial pressure, where DC motor pulls the piston rod according to the explained stiffness modulation methodology. The results of the first experiment showed that the valve performs well as a clutch and can be closed at any position. And in the case of shortening the total stroke length, the total force, maximum stiffness, and energy storage capacity are reduced. The results of the second experiment validate the hypothesis that higher initial equilibrium pressure leads to higher force, stiffness, and energy capacity. To conclude my talk, I presented a method for stiffness modulation using timely control of 3 valves in the proposed pneumatic quasi-passive mechanism. Mathematical model was tested through 2 experiments by changing the initial position and initial pressure. Future work will focus on the mechanical design of an exoskeleton exploiting the presented mechanism. Thank you for your attention, and I would like to thank my co-authors for their contribution.